Here are solutions to homework set number 4 for ECE 111. This homework looks at problems you run into in Math 129 linear algebra, how to solve them using Matlab. Well, Math 129 linear algebra is all about solving n equations and unknowns, and to do that, we use matrices. So for example, if I have two equations, two unknowns, I would first put that in matrix form, set my variables as x and y, and what this means, the first row is the first equation, so minus 14 times x plus 5 times y is minus 2. The second equation's the second row, minus 2 times x plus 14 times y is 3. Now in Matlab I can now solve, let's call that matrix B, matrix A. To input the matrix, it's the square bracket, start of matrix, minus 14, 5, first row, semicolon, minus 2, 14, second row, end of matrix. A is just minus 2, 3. The solution then is the inverse of B times A. So multiply everything on the left by B inverse. B inverse B cancels. B inverse A is now x and y. So there's my answer. Two equations, two unknowns. Now this you could do by hand. Where Matlab really shines, where matrix algebra really shines, stuff you cover in Math 129, is when you go beyond two equations, two unknowns. For example, three equations, three unknowns. Painful to solve by hand, pretty easy in Matlab. Just set up a matrix just like before. First equation is 2x plus 7y plus 2z is 1. Second equation, 16x plus 8y minus 12z is 7, and so on. There's your B matrix, here's your A matrix. Throw that in Matlab. So here's the B matrix, here's the A matrix. The solution is inverse of B times A. Works for four equations, four unknowns. Four equations, four unknowns. Make my unknowns A, B, C, D. Here's the first equation, second, third. Input the matrices into Matlab. And the solution is inverse of B times A. And kind of note, in this case, I did this in 4 steps, just because if there's a typo, it gets kind of annoying. So here's the first row, second row, third row, fourth row. Pack them all together, that's B. There's A. You know, many ways to input a matrix. So that's where Matlab really shines. Solving n equations and unknowns is really easy in Matlab, as long as you understand matrices. That's why Math 129 is required. What really matters at this point is get the equations right. If you get the equations right, then Matlab can solve them. You're also going to see that this is a recurring theme throughout the program. You're going to see this over and over again. If I can write the problem in the form of n equations and unknowns, I can solve. Problem 4. Suppose I have more unknowns than equations. In that case, you get least squares. For example, if you go to Bison Academy under 111, here are some data sets. If I click on them, this is the CO2 level versus year. Copy that, throw that into Matlab. I've got a whole bunch of data. And here's what the data looks like, the blue line. Let's come up with a curve fit. Try to come up with a parabolic curve fit that matches the data. The trick here is to set up your basis as, in this case, it's going to be year squared, year, and 1. My unknowns are the constants, times A times year squared, B times year, C times 1. To find A, it's least squares. That'll be the B transpose B inverse B transpose Y, or CO2 in this case. This is the least squares solution. We're going to be using that over and over again. The derivation of it is in the lecture notes. But once you get the data, I can do a curve fit. So let's do a parabolic curve fit for CO2 levels versus year. If you do that, import the data into Matlab, pull up the third column for year, fourth column for CO2 levels, throw that in as your basis, calculate the unknowns, there's your curve fit. Now to plot it, let's plot year versus CO2 levels in blue, year versus curve fit. So again, B is this, here's A, so this together is actually AY squared plus by plus c. That's the matrix form of it. Plot the curve fit in red, and here's what you get. Blue is the data, red is the curve fit. That matches pretty well. Once you get the data, I can answer questions, such as when will the CO2 levels reach 500 parts per million? So back in the graph, I can see the curve. Here's 420, 440, 500 is up here somewhere. Well, in Matlab, there's a roots command. Roots finds function equals 0. I don't want roots equal 0. I want roots equal 500. So subtract the 500. So this is y squared, y, and 1. Subtract 500, and when this is equal to 0, is when y is equal to 500. And the answer is 2051 plus a straight solution. When will the CO2 levels reach 2000? That's the year 2288 plus a straight solution. Okay, let's look at temperatures. Here's the Fargo temperature from Hector Airport. Let's do a linear curve fit. So in that case, I'm going to pull in the data. The year is the first column. The degrees Fahrenheit is the seventh column. This is January, February, March. Seventh column is June. Set up your basis. The basis is year and 1, because I'm trying to put it in this form, or in matrix form. It's year and 1 times A and B. That's the matrix version of it. And that's your basis times A. To find A is, again, least squares. Inverse of B transpose B, B transpose Y. So here's your curve fit. This is the slope. So if I plot it, year versus data, year versus curve fit, this is what I see. There's my linear curve fit showing that June actually is getting warmer. We can measure that in Fargo. I can see how much has changed. Here's the slope, the first term. The slope over 80 years is 4.98. Fargo's gotten about 5 degrees Fahrenheit warmer in the last 80 years. If I extrapolate out in the year 2050, here's the equation. If I plug in 2050, A times year plus B is 70.2. In year 2100, 73.3. We can start predicting based upon data. Problem 6 and 7, look at Arctic sea ice. Go to the National Snow and Ice Data Center. You can pull in data. If I want to do a linear curve fit, I'll pull in the data. First column is year, second column is ice level. That's the minimum. Set up your basis. Again, I'm going to write this in matrix form. That's going to be the matrix year and 1 times A and B. There's my basis function. Least squares curve fit. Same equation one more time. I get my curve fit. There's A and B. From this, I can find out when will your function equal 0. That's the roots command in Matlab. This says, assuming a linear curve fit, meaning nothing's changing, same ice melt every year, we should be ice-free in the year 2073. That's what your data looks like. If I assume a parabolic curve fit, same procedure, just change the basis to year squared, year, and 1. Least squares curve fit gives me 3 terms. This is your A, there's B, there's C. If I find the roots of A, this is when we'll be ice-free, assuming a parabolic curve fit, 2054, first time in 5 million years. And this is what the data looks like. If I plot the data versus curve fit, the red line is curve fit, you can see a slight bend to it. That's the parabolic curve fit. That just means the ice is melting at an increasing rate. Global temperatures. If you go to NASA Goddard has been keeping track of world temperatures since 1880. Bring in that data. If I want to do a linear curve fit, bring in the data. Do a linear curve fit. Here's your basis, linear curve fit. There's A and B. So if I do 1880 to 1910, here's what the curve fit looks like. Actually, it looks like we're getting colder. That actually was the worry back at the turn of the century, are we entering another ice age? Well, if we take more recent data, 1970 to 2022, do a parabolic curve fit, here's the data. You'll pull in that set of data. Do a parabolic curve fit, least squares, do a least squares curve fit, here's your A, B, and C. Plot the data. So this is 1970 to 2020. A little bit of a bend to it. Means we're getting warmer at an increasing rate. I can also ask questions such as, when will we be 10 degrees Celsius warmer? That's the roots command. What are the roots of A? Shifted by 0, 0, 10. So again, this is year squared, year, and 1. 10 is 0y squared plus 0y plus 10. Should be in the year 2276. Finally, the last problem. Normally don't grade the last problem. It gets too political. But just to give an idea what the data is meaning, if you go to different websites, they've done modeling on global temperatures. What happens at different temperatures? At 1 degree Celsius, we've already hit that, you should have increased heat waves in France, flows of rivers start to decrease, crop production decreases. At 2 degrees, based upon the current data, that'll be in the year 2067. Oceans absorb less CO2, soils start to release CO2, vacations to the Mediterranean, or Caribbean for us, are just too hot. Start getting crop failures in Africa and Central America. 3 degrees, you start getting crop failures in China, meaning 1 billion people are on the move. Collapse of equatorial governments. 4 degrees, Spain becomes a desert, Mexico becomes a desert, mass migrations to northern latitudes. The rainforests start to burn up. 6 degrees, ice caps are gone, methane hydrates become unstable, raising temperatures in positive feedback loop, ocean circulation stops, hydrogen sulfide gas producing bacteria start to flourish, poisons the air, ozone layer dissipates. Basically really, really bad. This is kind of scary. And this isn't just experts. If you just take the data is available to everyone. Take the data, analyze it yourself. The data is saying that we're approaching a cliff. If we can see the cliff, maybe we could do something to avoid it. And there are things we can do. That is week number 5 in 111. But that's homework set number 4, curve fitting. The main point behind it is with Matlab, I can curve fit just about anything. If I have n equations and unknowns, Matlab is really good at solving those. If I have more equations than unknowns, typically for data, lab data, I can use least squares curve fit and curve fit the data. That is homework set number 11, or correction, homework set number 4 for ECE 111.